Dear students, today we will discuss rotor of synchronous machines. So basically we have two types of rotors used in synchronous machine. One is salient type rotor and another one is non-salient. Non-salient type rotor. So salient type rotor, this is also known as cylindrical. Rotor, non-salient rotor or cylindrical rotor. So we have various type of application depending upon the requirement of a speed. If we need high speed rotor, then we will use non-salient or cylindrical. Here number of poles will be 2 or at max 4. In case of salient type rotor, number of poles will be minimum 4, 6, 8 and so on, 4 onward. In case of P is equal to 4, if our frequency is 50 Hz as in case of India, so if you are going to calculate a speed of rotor required to generate an EMF of frequency 50 Hz, so for a 4-pole structure we may substitute 120 F by P. We know this speed can be evaluated by this 120 times 50 upon 4. So 3 times 30, that is 1500 RPM. If we are going to increase pole from 4 to 6, then this will be lesser than 1500 RPM and so on. By increasing number of poles, the speed will be lesser and lesser and lesser. So we can say that the requirement of a speed from low up to 1500 RPM will need a rotor of this type, salient. On the other hand, in case of turbo generator, if we are going to substitute P is equal to 2, for 4 it will be this 1500 RPM, but for P equal to 2 it will increase to 3000 RPM for 50 Hz. If we are going to increase for 60 Hz, so it will be even more than this. So depending upon the requirement of a speed, we have the two types of rotor used in synchronous generator. So we will discuss one by one. First we will discuss salient type rotor of alternator, then non-salient or cylindrical rotor. So as we know that for salient rotor we have number of poles minimum 4 onward. So a typical 4-pole rotor is shown here. See, number of poles: north pole, south pole, north pole, south pole. We can't have 2-pole structure for salient pole. Why? For 2-pole the speed will be very high. Even for 50 Hz, not 60 Hz, even for 50 Hz it will be 3000 RPM. That will create a huge centrifugal force which may damage the rotor structure. If force is excessively high, then this structure will not sustain. So in that case we will use cylindrical rotor, which we will discuss in detail later after this. So now come to this salient pole rotor. So this will be 4, 6, 8 and so on. What we can note that we have concentrated windings on this body. This body is known as pole body. So on this body we can say, we know what does it mean by dot and cross notation. So we have one concentrated winding in which DC supply is provided. DC supply will be given, then DC current will flow if circuit is completed. Once DC current is flowing, so corresponding fluxes will be there. So we know that here north pole will be created. We are creating this north pole. If we will reverse this direction of current in this coil, similar coil on some another pole body, see here we have reversed the direction. Here first dot is there, then cross. This side first cross is there, then dot. We can see, right? So flux produced by this winding in which DC field current is provided will have direction as shown, right, with red dotted lines like this. So we can say that here we have produced south pole effect as the direction of flux lines may be observed. I have shown just few lines for representative case. You know that through this body the path having minimum reluctance will have more and more fluxes. So one closed loop will be formed as shown, creating north pole here, south pole here. Again we can create north pole here and south pole here, means we are going to create poles alternately, one north then south, north south. Why? We will discuss it later, but as far as construction is concerned, we will focus on the orientation of various parts of rotor and their reason behind it. So far we have discussed that we have concentrated winding on each pole body. These are pole body. You may write, if you want, you may write this as pole body. So on each pole body we have field windings, and each field winding is series connected to form a single winding. The winding associated with each pole is further connected in series to form a single field winding. So we have single field winding and we may represent it like this, plus minus something like that, and whatever current is flowing through this we may represent IF, means the same field current which is having constant value DC in nature is flowing through each coil associated with each pole, creating alternately north and south pole depending upon our requirement. Here we have considered a typical 4-pole structure. The same can be understood for 6-pole structure, for 8-pole structure, even for 10-pole structure. Alternate north and south pole are being created by a single field winding. Now what happens next? Once you are going to rotate this rotor by means of any prime mover, the associated field MMF will also rotate. These MMF will link to the stator winding discussed yesterday. Here I have not shown the detail of slots and the stator winding. This is the stator part. In between air gap is there. So the conductors placed on a stator will experience that flux are cutting once you are going to rotate this rotor, as you have given DC supply here. So corresponding field is there. Once rotor is being rotated, windings are also being rotated, and you have provided supply, though DC in nature, but once it is rotating, the conductors placed on a stator will experience varying flux with time. So as per Faraday's law of electromagnetic induction, we know that EMF will induce in the stator windings. Good, but thing is that the generated EMF so induced in a stator winding is required to be sinusoidal in nature. This is our requirement. But the MMF produced by this field winding, you know what is MMF? So MMF is nothing but N into I. If you have one coil of N turns and current is I, so here as discussed, I is constant in nature, N is number of turns fixed, so MMF will be fixed. So if MMF is fixed, so the nature of flux density in the air gap will not be sinusoidal. So to have that sinusoidal effect, what we will do, we are going to have the shape of our poles like this. See, this is a stator and I am showing one pole. So here you can observe that the air gap in the center is minimum. Why I am doing this will be explained later. First observe that the air gap in the center is minimum. As you are moving away from the center, the air gap is increasing and you can see that at the end it is maximum as you are moving. What is the reason behind this? This shape of pole is known as chamfering. You can say chamfered pole, chamfering of pole. So why we need to have to chamfer a pole in case of salient pole rotor? The portion where air gap is minimum, reluctance will be minimum, and the portion where air gap is more, reluctance will be more. So what will be effect on fluxes? We know that flux may be written as MMF upon reluctance, that is Ni. MMF we have fixed constant for our setup, constant number of fixed number of turns and DC nature of current. But by varying R, reluctance phi will vary. So where phi will be more, where R is less. Where R is less, reluctance, we will say reluctance sometimes denoted by S also. So this is reluctance. So the position, central position where air gap is minimum, reluctance will be minimum, so flux density will be more. And the position where air gap is more, reluctance will be more, hence flux density will be minimum. So we can say that we have now a varying flux distribution, not constant. And you may further observe that for this shape, that distribution is having a sinusoidal nature. So depending upon the amount of that, extent of that sinusoid, you can vary the gaps. You can design different structures. Suppose sometimes this is also sinusoidal, this is also sinusoidal, this is also sinusoidal. So depending upon your requirement of peak value or depending upon your form factor maximum value, whatever, we have different design of such varying air gap for our salient pole. So far we covered why we need chamfered pole. What is the reason behind this? Now the generated EMF will be somewhat of sinusoidal nature, not pure sinusoid. We will never get a pure sinusoidal wave shape, but up to some extent we can have similar EMF generated. So what will be its effect? If we don't have pure sinusoidal generated EMF, then it will contain one fundamental component and some harmonics. We don't want harmonics, we don't want disturbances at any cost, right, in signals also. So to reduce those unwanted harmonics, we do some other things which will be discussed later, like distribution. One part is we discussed that stator windings are distributed in various slots. So this is also one of the reasons to reduce these unwanted harmonics. Short chorded winding, we use short pitching, right, fractional slot. So these are the additional steps taken to make our generated EMFs in the stator winding nearest to sinusoid. Fine. Now come to the pole shoe. This portion, upper portion is known as pole shoe. See the structure, the shape is somewhat like shoe. So name is pole shoe. This is body, pole body, this is pole shoe. So in pole shoe, holes are drilled. We are talking about salient pole structure. So holes are drilled on pole shoe, just write here pole shoe, and copper bars are inserted in these holes. So on each pole we have copper bars inserted on the pole shoes, and these copper bars are brought out together, connected at both the end by end rings. So you will have a structure similar to that of a squirrel cage rotor of 3-phase induction machine. So why we are doing this? The reason behind this, having copper bars inserted on pole shoe and connected at both the ends with the help of end rings and forming a structure similar to that of a squirrel cage rotor of induction machine is point number 1. In case of any disturbance, now you have alternator, working alternator generating EMF connected to the system, power system, with the help of transformer or sometimes directly, whatever. So this is a part of system. So in case of any disturbance at any part of the system to which this alternator is connected, this will experience oscillation. Rotor will experience oscillation. So we need to damp out these oscillations. So these are helpful, such structures are helpful in damping out of oscillations in case of disturbance. Suppose sudden load change, that is also a disturbance, type of disturbance. So this is one of the advantage of having copper bars, damper bars, also known as damper bars, the advantage of damper winding. Second advantage, when our synchronous machine is used as synchronous motor, so at that time it helps in starting the motor, similar to that of induction motor. How? When we are going to use our machine as a motor, it means we have input as electrical supply, 3-phase balance winding is supplied with 3-phase balance supply. So rotating magnetic field is produced, rotor is stationary. So copper bars are there in which EMF will induce, and these bars are shorted, means circuit is complete, so corresponding current will flow. Those conductors, current carrying conductors will experience force because rotating magnetic field is there. Again, as per Faraday's law of electromagnetic induction, relative motion will be observed by the conductors on the rotor. So EMF is induced, current is there, force is there, and it will start rotating. Once it will attain a speed corresponding to synchronous speed, means it has reached synchronous speed at which the relative speed between these conductors, damper bars, and rotating field will be 0, as both are rotating at synchronous speed. See, rotating magnetic field is rotating at synchronous speed, and once the rotor has attained synchronous speed, so there will be no relative speed between the damper bars and rotating field. At that time no EMF will be induced, so at that time it will not affect the running condition of the motor. Fine. So these are the two reasons to have holes drilled on pole shoe and copper bar to be inserted in this. Fine. So now next we will discuss the another type of rotor which is cylindrical, that is non-salient. This part is known as yoke. For small machines this is made up of cast iron, but for larger machines we can use laminated structure.